proof. To be successful with this topic, you need to be good at algebraic manipulation. For example, you need to be able to expand a triple bracket. I'm not going to reteach this topic in this video, so if that's something you need to work on, you may want to watch that video first. I'll put a link to that one in this video's description. So assuming you are comfortable with expanding triple brackets, let's talk about algebraic proof. There are many different styles of algebraic proof question. In this video I'm going to go through lots of examples, these 16 in fact, to give you good coverage of the different types of questions you could face. We're going to start with this question here. I like to call this type of proof an LHS equals RHS proof, or left hand side equals right hand side. That's because in this proof we've got something on the left hand side and we need to show it's equal to something else on the right hand side. When we answer a question like this, we're going to start with the left hand side and then we're going to end up with the right hand side by doing some algebraic manipulation along the way. So let's do this as our first example. We're going to start with the left hand side, which is this, and then we're going to manipulate it so that we end up with what's on the right hand side. So we're going to first of all look at this part here, n plus 4 all squared, which means n plus 4 multiplied by itself. So this is equal to n plus 4 multiplied by n plus 4. And then we have minus 3 lots of n plus 4. Now what we're going to do is expand this out. We'll expand these double brackets here first. To do this, we do n times n, which is n squared, n times 4, which is 4n, 4 times n, which is also 4n, and 4 times 4, which is 16. Then we can expand this single bracket here. Negative 3 times n is negative 3n, and negative 3 times positive 4 is negative 12. Now that this is expanded, we can simplify by collecting like terms. So we have n squared, and there's no other n squared, so it's just 1n squared. Then we have 4n plus 4n and subtract 3n. 4 add 4 is 8, subtract 3 is 5, so we have 5n. And then for the constants, we have 16, subtract 12, which is 4, so plus 4. We've now ended up with a quadratic expression which we can factorize. We're looking for two numbers that multiply to make 4, but add to make 5. And that's 1 and 4. So we can factorize this as n plus 1, n plus 4. Which is exactly what was on the right hand side. So we've now finished the proof. So if you look closely here, we started with this, which was exactly what was on the left hand side. And then we ended up with this, which was exactly what was on the right hand side. Let's have a look at another example of a left hand side equals right hand side proof. So this time we're going to prove this. So we're going to start with what's on the left hand side, and we're going to manipulate this so that we end up with the right hand side. So if we start with 2n plus 3 all squared, that's 2n plus 3 multiplied by itself. Then we need to subtract from this 3 lots of n minus 1 n plus 2. So let's expand this double bracket here first. 2n times 2n is 4n squared. 2n times 3 is plus 6n. 3 times 2n is also plus 6n, and 3 times 3 is plus 9. Now we come to this part here. The way we want to approach something like this is writing negative 3, then a large bracket. Then we'll expand the double bracket and write the result inside this large bracket. We need to be really careful here to make sure we don't make mistakes with signs. So we're going to start with n times n, which is n squared, n times 2, which is plus 2n, and negative 1 times n, which is negative 1n, and a negative 1 times a positive 2, so negative 2. Then we'll just simplify this part here. So we have 4n squared. If we add the two 6n's together, we get 12n, and then plus 9. But for this part here, we're now going to multiply that entire bracket through by negative 3. So it's negative 3 times n squared, or negative 3n squared, negative 3 times positive 2n, so negative 6n, negative 3 times negative n, and two negatives multiplied gives a positive, so positive 3n, and negative 3 multiplied by negative 2, so positive 6. We can now simplify by collecting like terms. So in n squared, we've got 4n squared minus 3n squared, which is 1n squared. We've got 12n minus 6n plus 3n, which is plus 9n. And then we have 9 add 6, which is 15. Now the right hand side for this example is a little bit different. We have a double bracket, but then we also have plus 1. If we look at this double bracket here and imagine expanding it, we'll get n squared plus 7n plus 2n, which will give us plus 9n, and then plus 7 times 2, which is 14. We just have a plus 15 rather than a plus 14, but that's why there's this plus 1 here. The best way to show this is rewrite what we have as n squared plus 9n plus 14, since we know that's what we'd get if we expanded the bracket, and then plus 1. You could almost think of this as unsimplifying the 15 into a 14 plus 1. We now know that this part here will factorize to give n plus 2, n plus 7, and then we have a plus 1 on the end. And that's the proof complete. We started with this here, which was our left hand side, and then we ended up with this here, which was our right hand side. In this next proof, it's going to specify that n is a positive integer with n greater than 1. And we're going to prove that this is a multiple of 12. So this is a very different type of proof. Let's talk about what it means to be a multiple of 12. The multiples of 12 are the numbers in the 12 times table. So if you multiply 12 by any integer, you'll get a multiple of 12. For example, 12 times 1 is 12, that's a multiple of 12. 12 times 5 is 60, that's a multiple of 12. In fact, 12 multiplied by any integer will give a multiple of 12. Since in this question we're told that n is an integer, we could replace the word integer here with n. So 12 times n, which is 12n, must also be a multiple of 12. In fact, 12 multiplied by 3n squared plus 2n plus 5 will also be a multiple of 12. This is because 3n squared plus 2n plus 5 must be an integer, and 12 multiplied by any integer will give you a multiple of 12. We're going to use this idea in this proof. So we're going to start with the expression we're given, and we're going to try and manipulate it so that it's a multiple of 12. So let's first of all expand these brackets. We've got n plus 4 all squared, which is n plus 4 times by itself, and then we need to subtract from this n minus 2 multiplied by itself. If we start with this first double bracket, we have n times n, n squared, n times 4, 4n, 4 times n, also 4n, and 4 times 4, 16. Then when we come to do the second bracket, just like the previous question, we're going to need to be careful with the signs here. We're going to write a negative, then a big bracket, then when we expand these two brackets, we'll put the result inside that bracket. So we'll do n times n, n squared, n times negative 2, negative 2n, negative 2 times n, negative 2n as well, and negative 2 times negative 2, positive 4. We can simplify this quadratic here, it will be n squared plus 8n plus 16, and then we need to expand out this bracket. Since there's no number in front of the bracket, you could think of that number as being negative 1. So negative 1 times n squared is negative n squared. Negative 1 times negative 2n is positive 2n. The same for the next term. And negative 1 multiplied by positive 4 is negative 4. Now we can go ahead and simplify. We have n squared subtract n squared, which is actually 0. Then we have 8n plus 2n plus 2n, which is 12n. And then 16 subtract 4, which is plus 12. Now this is not surprising that we've ended up with 12s here, since we're trying to show it as a multiple of 12. To do this properly, you now need to factorize this expression. So we're going to factorize out a 12. So it'll be 12 lots of n plus 1. Since when you expand 12n plus 1, you get 12n plus 12. Now we know in this question that n is an integer. So this part here, n plus 1, must also be an integer. Therefore, we've got 12 multiplied by some integer, which we know must be a multiple of 12. So we can finish this proof by writing down a sentence. N plus 1 is an integer, so 12 lots of n plus 1 must be a multiple of 12. Let's try another example a bit like this one. So once again, we have n being a positive integer, but this time we're going to prove that this is a multiple of 10. So let's take the expression, and if we start with the 3n plus 2 all squared, that's 3n plus 2 multiplied by itself. Then we subtract from this 3n minus 2 multiplied by itself, and then we're also going to add 2 lots of 3n plus 5. So let's expand this bracket here first. 3n times 3n is 9n squared. 3n times 2 is plus 6n. 2 times 3n is also plus 6n. And 2 times 2 is 4. For this next bracket, we're going to do that idea again, where we write one big bracket and write the answer to that expansion inside it. This prevents us from making any errors with our signs. So we have 3n times 3n, which is 9n squared. 3n times negative 2, negative 6n. Negative 2 times 3n, also negative 6n. And negative 2 times itself, which is positive 4. Then right at the end here, we have to expand this bracket, which we can do now. 2 times 3n is 6n, and 2 times 5 is 10. Next, if we simplify this quadratic here, we've got 9n squared, 6n plus 6n is 12n, and then plus 4. Then if we move on to this bracket here, we need to expand this out. Imagine there's a negative 1 at the front of the bracket. Negative 1 times 9n squared, negative 9n squared. Then we have plus 6n, subtract 4. And then of course we've got these two terms on the end as well, plus 6n plus 10. So we now need to simplify all of this. So we have 9n squared, subtract 9n squared, which is 0. And then we have 12n plus 6n plus 6n plus another 6n, which will give you 30n. And then we have 4, subtract 4, which would be 0, and then plus 10, which is plus 10. So remember in this question we were trying to show it was a multiple of 10 this time. To do this we need to factorize out to 10. So it'll be 10 lots of 3n plus 1. Since 10 multiplied by 3n plus 1 is the same as 30n plus 10. So just like in the previous proof, since n is an integer, 3 lots of n plus 1 is also an integer. So we can finish this proof by writing 3n plus 1 is an integer, so 10 lots of 3n plus 1 is a multiple of 10. In this next proof, n will be a positive integer again, and we're going to prove that this is even. So what do we mean by an even number? Well, even numbers are 0, 2, 4, 6, 8, 10, and so on. In fact, the negative versions of these are also even, so negative 2, negative 4, negative 6, and so on. Notice how the even numbers here are just the numbers in the 2 times table. So to show a number is even, we just need to show that it's a multiple of 2. So just like we did for multiples of 12 or 10, we're going to show that this is a multiple of 2, which is therefore even. So let's take this expression, and we're going to show that it's a multiple of 2. So we'll start by expanding these brackets here. N times n is n squared. n times negative 2, negative 2n. 2 times n is 2n. And 2 times negative 2 is negative 4. Then for this bracket, we have n times n, which is n squared, and n times 6, which is 6n. Then if we do some simplifying, we have n squared plus n squared, which is 2n squared. We have negative 2n plus 2n, which would be 0, and then plus 6n, so just plus 6n. And there's only one constant here, negative 4. So we're trying to show that this is even by showing it's a multiple of 2. So we need to factorize out a 2, and we can now do that. So this would be 2 lots of n squared to get the 2n squared, 3n to get the 6n, and negative 2 to get the negative 4. So just like the last two proofs, we can now write a statement. N squared plus 3n minus 2 must be an integer, which means that 2 lots of that is a multiple of 2. But we know that a multiple of 2 also shows that the number is even. And that's the proof complete. What about if instead we had to show that a number was odd, like this one here? By odd numbers, we mean the numbers 1, 3, 5, 7, 9, 11, and so on, and also the negative ones, negative 1, negative 3, and so on. Notice how all of the odd numbers are just one more than an even. For instance, the number 1 is one more than 0, which was even. The number 3 is one more than 2, which is even. The number 5 is one more than 4, which is even. So all odd numbers are just one more than an even number. So to show a number is odd, we need to show it is one more than an even. Let's now try this question with this in mind. So let's take the expression and we'll start with this double bracket here, which is 2n minus 3 multiplied by itself. And then we also have plus 4 lots of n minus 2. So let's expand this bracket. 2n times 2n is 4n squared. 2n times negative 3, negative 6n. Negative 3 times 2n is also negative 6n. And negative 3 multiplied by negative 3, positive 9. For the single bracket, we've got 4 times n, 4n, and 4 times negative 2, negative 8. Now that we've expanded, we can do some simplifying. So we've got 4n squared and no other n squared, so it's just 4n squared. We've got minus 6n, which would be minus 12n, plus 4n, which would be minus 8n. And then we've also got 9, take away 8, which is just 1. Now remember, we're trying to show this one's an odd number. And I said to show something's an odd number, we need to show it's one more than an even number. We've got a plus 1 here at the end, so if this number's going to be odd, this part here must be even. So if we show this is even, and we add 1 to it, we must have an odd number. We can show this is even by showing it's a multiple of 2. And to do that, we factorize out a 2. So we write this as 2 lots of 2n squared minus 4n, and then we have this plus 1 at the end. So we know that 2 lots of 2n squared minus 4n must be even, since it's a multiple of 2, which means if we add 1 to that and do 2 lots of 2n squared minus 4n plus 1, it must be odd. And that's the proof complete. For this next proof, we're going to have n as an integer, and we're going to prove that this is always a square number. A square number is the result of multiplying an integer by itself. So we need to end up with something that's an integer times by itself. So let's take this expression and see what happens. If we expand out this part, we get n times n squared, n times 6 plus 6n. Then negative 2 times n, which is negative 2n, and negative 2 times negative 2, positive 4. If we simplify this, we have n squared, and then we have 6n take 2n, which is 4n, and then plus 4. Now at this point it's not immediately obvious why this is a square number, but we could factorize this. It would be n plus 2, n plus 2. But n plus 2 times n plus 2 is the same as n plus 2 squared, since it's n plus 2 multiplied by itself. We've now shown that this is a square number because n plus 2 must be an integer, and when you multiply that by itself, you'll end up with a square number. So we can finish this proof by writing n plus 2 as an integer, so n plus 2 squared is always a square number. In the next proof, n is going to be a positive integer, and we're going to prove that this is a cube number. So this is quite a long question. We're going to start by taking the expression, and I'm going to multiply 4 by 4n plus 5, which will give me 16n minus 20. Then I'm going to expand this double bracket here and write the result inside a large bracket. 4n times n is 4n squared. 4n times 1 is 4n. 1 times n is 1n. And 1 times 1 is 1. Then we could also expand out this bracket here. 4 lots of 21n is 84n, and 4 lots of 5 is 20. Then if we keep the first bracket the same, so 16n minus 20, and then inside this bracket we could simplify, 4n plus n is 5n. So inside that bracket we have 4n squared plus 5n plus 1, and then plus 84n plus 20. We're now going to expand out these brackets. So we need to multiply everything in the first bracket by everything in the second bracket. To do this, I'll multiply 16n by all of the terms in the second bracket, and then negative 20 by all of the terms in the second bracket as well. So 16n times 4n squared is 64n cubed. 16n times 5n is 80n squared. And 16n times 1 is 16n. Then for negative 20, we have negative 20 times 4n squared, negative 80n squared, negative 20 times positive 5n, negative 100n, and negative 20 times positive 1, negative 20. And then we also have this plus 84n plus 20 at the end. Now we need to simplify this. So in terms of the n cubed, there's only one term, 64n cubed. Then we have 80n squared minus 80n squared, which will be 0. Then 16n, subtract 100n plus 84n, which will also be 0. And then negative 20 plus 20, which is again also 0. So this is just equal to 64n cubed. In this question, we're trying to show it's a cube number. And you might think we finished, but we do need to do one more step. We need to write this as something to the power 3. Now 64n cubed is the same as 4n times 4n times 4n. Since 4 times 4 times 4 is 64, and n times n is n cubed. So this is the same as 4n to the power 3. Now 4n must be an integer, so 4n to the power 3 must be a cube number. So we can finish this proof by saying 4n is an integer, so 4n to the power 3 is always a cube number. In this next proof, n is a positive integer again, and we're going to prove that this is one more than a multiple of 3. Now this is quite similar to the way that we proved something was an odd number. Odd numbers were one more than an even number, or one more than a multiple of 2. So to prove something's one more than a multiple of 3, we use the same sort of approach. So let's take this expression, and we'll start with n plus 1 squared, which is n plus 1 times itself, and then we have plus n lots of 2n plus 1. Let's get expanding. N times n is n squared, n times 1 is plus n, 1 times n is also plus n, and 1 times 1 is 1. Then for the second bracket, we have n times 2n, which is 2n squared, and n times 1, which is n. When we simplify, we have n squared plus 2n squared, which is plus 3n squared. Then we have n plus another n, so that's 3n. And then just plus 1 here, so plus 1. Now we're trying to show this is 1 more than a multiple of 3. So we have this plus 1 here, which means that this part here must be the multiple of 3. And it quite clearly is because we can factorize a 3 out. So this part is the same as 3 lots of n squared plus n, and then we have plus 1. So the 3 lots of n squared plus n is a multiple of 3, so when we add 1 to it, it must be 1 more than multiple of 3. So we can finish this proof by writing 3 n squared plus n is a multiple of 3, which means that 3 lots of n squared plus n plus 1 is 1 more than a multiple of 3. And that's the proof complete. Let's try another one that has a similar feel to that one. N is a positive integer, and we're going to prove that this is 1 more than a multiple of 5. So we'll start by expanding the double bracket. 3n times 2n is 6n squared. 3n times 3 is plus 9n. 4 times 2n is 8n, and 4 times 3 is 12. Then for this bracket here, we're going to write a negative, then a large bracket, and expand the double bracket and write the result inside there. So n times n squared. N times negative 4, negative 4n. 1 times n is 1n, and 1 times negative 4, negative 4. Now we can simplify a little bit here. We've got 6n squared. 9n plus 8n is 17n, and then plus 12. Then here we multiply through by negative 1. So negative n squared plus 4n, subtract n, and plus 4. If we simplify, 6n squared minus n squared is 5n squared. 17n plus 4n minus 1n is 20n. And then 12 plus 4 is 16. So we're trying to show that this one is 1 more than a multiple of 5. But this time we don't have that plus 1 at the end. So we're going to need to unsimplify the 16 so that it does have a plus 1. So we'd write this as 5n squared plus 20n, but then plus 15 plus 1. Obviously 15 plus 1 is 16, but we now have that plus 1 at the end. So if this is to be 1 more than a multiple of 5, those first 3 terms must be a multiple of 5. Unfortunately, they are. We can factorize out of 5 to show that, so it'll be 5 lots of n squared plus 4n plus 3. And of course, plus 1 at the end. So we can finish this proof by saying that 5n squared plus 4n plus 3 is a multiple of 5. So 5 lots of n squared plus 4n plus 3 plus 1 is 1 more than a multiple of 5. Now we're going to move on and have a look at some different proofs. For this one, prove that the sum of 4 consecutive integers is even. The new part for this proof is the idea of 4 consecutive integers. Consecutive integers are whole numbers that follow on from each other. For example, 1, 2, 3, 4. 13, 14, 15, 16. 87, 88, 89, and 90. They're all consecutive because they follow on in order. So what does this look like algebraically? Well, if we take our first integer to be n, then the next one is n plus 1, the one after this is n plus 2, and the one after this is n plus 3. So this is how you would write down 4 consecutive integers. The question says to do the sum of 4 consecutive integers, so we need to add these together. So if we add these together, we can simplify n plus n plus n plus n is 4n. Then we have 1 plus 2 plus 3, which is plus 6. In this question, we've been asked to show that this is even. To show it's even, we'll show it's a multiple of 2. So we can factorise out of 2 here, it's 2 lots of 2n plus 3. So we can now finish by saying that 2n plus 3 is an integer, so 2 lots of 2n plus 3 is even. Let's try a second example like this. So this time we're going to prove the sum of 3 consecutive integers is a multiple of 3. So for our consecutive integers, we're going to have n, the second one, which will be n plus 1, and the third one, which will be n plus 2. And we're adding these together again, and we need to show it's a multiple of 3. So if we add n and n and n, we get 3n, and if we add 1 and 2, we get plus 3. So we just need to show this is a multiple of 3 by factorising out a 3. So it's 3 lots of n plus 1. So we can finish this proof by saying n plus 1 is an integer, so 3 lots of n plus 1 is a multiple of 3. Now let's look at a slightly harder version of this type of proof. So this time we're going to prove the product of 3 consecutive even numbers is a multiple of 8. So if we look at 3 consecutive even numbers, you might be thinking of doing n plus 1 and n plus 2. But the problem with this is if we had these numbers, they would be consecutive but not necessarily all even. For instance, if n was 3, we'd have 3, 4 and 5. Here we've only got one even number. If n was 10, we'd have 10, 11, 12. And here we have 2 even numbers. So this isn't how you write down 3 consecutive even numbers, it's just 3 consecutive numbers. To do 3 consecutive even numbers, we need to first of all start with 2n. 2n is a multiple of 2, so we can guarantee it's even. If we have an even number, to get the next even number, we would need to add 2. For example, if your even number was 12, you would add 2 to it to get 14. So the next even number after 2n is 2n plus 2. The next even number after this one is 2n plus 4, since we add 2 once more. So this is how you write down 3 consecutive even numbers. Just for interest, if it was 3 consecutive odd numbers, you do 2n plus 1, since that's guaranteed to be odd since it's 1 more than an even, add 2 to this one, so 2n plus 3, and then add 2 to this one, 2n plus 5. But this question was 3 consecutive even numbers, so we'll go with those. Now this question also says the product, so it's not the sum this time. Product means multiply, so we need to multiply these numbers together. To do that, we would write them in brackets like this. We'll start by expanding this double bracket. So we have 2n, and we'll write the result of our expansion inside this big bracket here. So 2n times 2n, 4n squared, 2n times 4, 8n, 2 times 2n, 4n, and 2 times 4, 8. We could simplify the 8n plus 4n, so we've got 2n, 4n squared, plus 12n plus 8. We now need to expand through by 2n, so it's 2n times all of the terms in this bracket. 2n times 4n squared is 8n cubed, 2n times 12n is 24n squared, and 2n times 8 is 16n. So for this one, we've been asked to show it's a multiple of 8, so we need to factorise out 8. And we can, it's 8 lots of n cubed plus 3n squared plus 2n. We can finish this one by writing that n cubed plus 3n squared plus 2n is an integer, so 8 lots of that is a multiple of 8. Moving on to the next proof. This time we're going to prove that the product of any 2 odd numbers is odd. In the last proof we discussed how to write an odd number. It was 2n plus 1. So you might be thinking, great, I know how to do this, we also need 2n plus 3. But that would be if the numbers were consecutive odd numbers. But this question doesn't specify they're consecutive. It just says any two odd numbers. So it could be the number 1 and the number 187, or it could be 293 and 1491. Now we are going to use 2n plus 1 as our first odd number, but for the second odd number, we need to use a different letter because that second odd number could be different. So instead of 2n plus 1, we'll write the second odd number as 2m plus 1. This question said to do the product of these, so we're going to multiply them together. So if we expand out these brackets, we've got 2n times 2m, which is 4nm, 2n times 1, which is 2n, and 1 times 2m, which is 2m, and 1 times 1, which is 1. So we're trying to show that this one is odd. To show something's odd, remember, we show it's one more than an even. And to show something's even, we show it as a multiple of 2. So what we want to do here, since we have the plus 1 at the end, is factorize a 2 out of all of the other terms. So it's 2 lots of 2nm plus n plus m plus 1. So we can now be sure that this part here is a multiple of 2 and therefore even, and then when we add 1 to it, it will be odd. So we could say that 2 lots of 2nm plus m is even, and when we add 1 to that, we end up with odd. And now we're going to have a look at the final type of proof questions. So for this one, we're going to prove that this is always positive. When we say something's positive, we mean it's greater than 0. So we're going to take this expression, and to do this, we're going to complete the square. If you don't know how to complete the square or just want to revise it, I'm going to put a link to my video on it in this video's description, because I'm not going to explain it in detail now. So to complete the square on this, we have a bracket squared. We halve the coefficient of n, so -5. We then square that, which is 25, and subtract it, so subtract 25, and then we have this constant term plus 26 at the end. So this is n minus 5 all squared. We can simplify this part, -25 plus 26 is plus 1. Now that this is in the completed square form, we can show it's always positive. Let's start by looking at n minus 5 all squared. This is some integer squared. Now when you square an integer, it's impossible for it to be negative. Take a moment to think about this. If you square a positive number, like 3 times 3, you get a positive number, 9. If you square a negative number, like -3 times -3, you also get a positive number, positive 9. The lowest it could possibly be is 0. If you did 0 squared, you'd get 0. So this part here must be greater than or equal to 0. Positive 1 is obviously greater than 0. So what we have here is a number that's greater than or equal to 0, plus a positive number, which must be a positive number. So we can finish this proof by writing n minus 5 all squared is greater than or equal to 0, 1 is greater than 0, so n minus 5 all squared plus 1 must be greater than 0, which means it's positive. And now let's look at one more proof, which is a harder version of this one. So this time we're going to prove that this is always negative rather than positive. If something's negative, it must be less than 0. We will also complete the square to do this one. So if we take the expression, since this one has a negative n squared, I'm going to reorder the terms first. So we have -n squared plus 8n subtract 19. If you're completing the square but the n squared term is negative, it's easiest to factorize out -1 first. So we're going to write this as negative, then a large bracket. Then we're going to change all of the signs of all of those terms. So instead of -n squared, positive n squared. Instead of positive 8n, negative 8n. and then instead of negative 19, positive 19. So these two expressions are the same, one has just been multiplied by a negative 1. Now we're going to complete the square on what's inside the large bracket. So for n squared minus 8n, we halve the 8 to get negative 4, so it's n minus 4 all squared. We square negative 4, which is 16, and subtract it, and then we have plus 19. We can then simplify these terms here, so we have negative n minus 4 squared, negative 16 plus 19 is plus 3. Now we can multiply back through by negative 1. So we have negative 1 multiplied by this bracket, which is just negative lots of the bracket, and then negative 1 multiplied by positive 3, which is negative 3. Now for this one we need to show it's negative, which is very similar to what we did in the previous proof for positive. So we look at this part here. Now the bracket itself must be greater than or equal to 0, but since it's got a negative at the front, it must be less than or equal to 0. Negative 3 is obviously less than 0, so what we have here is something that's less than or equal to 0, and then we're subtracting a number from it, so it must be negative. To write this, we could say that negative bracket n minus 4 squared is less than or equal to 0, negative 3 is less than 0, so negative bracket n minus 4 all squared subtract 3 must be less than 0.